demo.
Yeah.
We just discussed about why you write the internal energy as proportion to n tilde square.
Right.
What is the meaning?
Well, the meaning, good question. I mean, well, dimensionally, I mean, you know,
What do you mean internal?
well, internal as opposed to, in other words, it's basically energy associated with the density fluctuation as opposed to energy associated with the fluid motion. In other words, look at it this way. I mean, I can write this. I mean, the analog is the way I would say it. Let's try ion acoustic for a minute. I always go back to ion acoustic as an example. How would you write the total energy for an ion acoustic wave? You'd write it something as 1/2 rho v tilde squared. And then you'd have something, you know, there'd be the compression, c sub s squared over times, this is kind of where the idea comes from, times what amounts to n tilde over n naught squared over 2, right? That, right?
The background physics.
What?
The physics background of the second term.
Well, I mean, look, if you have a wave that has got to have some, this in ion acoustic, this is clear because it's compression drives the wave. Okay, so I mean, if you write the equations of motion, you'd have something like d by dt of v is equal to something like cs squared times d by dx of rho, and you might absorb, or n, or things like this. And you would also have a density equation, d by dt of n, well, it would be in 1D, it would be something like this, d by dx of v, right? So you might ask, how could I form a kind of, you know, the way I always like the thing is, how can I form something like an energy theorem for this? Right? And the way you do it is, of course, if you multiply this by v, then here you got to multiply this by n, ultimately, right? And actually by cs squared times n. Right, so then what you get is d by dt of rho naught v tilde squared over 2 plus cs squared n tilde over n naught squared. Right, this is your energy density. So I mean, you can think of this as a fluctuating internal energy in some sense, right? This is, and then by the way, you'd have also, and you'd have something like d by dx of n tilde v tilde. And there'd be some c sub s squared. This is the energy flux. All right, so that's the, this is the energy density. So you can think of this as, I call this an internal energy, and this is a kinetic energy. It's an internal energy in the sense, it goes essentially as a pressure, right? Only the pressure is, you know, it's got to be quadratic, and so it's c sub s squared times n tilde over n naught squared. And then this thing in the drift waves is effectively the same story as that. You know, in other words, it's basically, I'm constructing in the drift, I forgot, I've been taking rho naught here for one, okay, here, but if I was more careful, I'd have d by dt of rho naught v cross d, that's your kinetic energy, right, over 2. And then my fluctuating internal energy would be this other guy, n tilde Well, it would be C sub s squared times rho naught, which would be TE over, which would be TE times n tilde over n naught squared. Okay, and let me show you why another way to see there has to be something like that. What happens in the Boltzmann limit? Right, in other words, n tilde over n goes to e pi over t, right? Right. Well, let's look at the Hasegawa-Wakatani equation in the Boltzmann limit. Okay. So, not the Hasegawa limit, excuse me. In the Boltzmann limit, it's d by dt of phi minus rho s squared. Well, I mean, it's total derivative here, but it'll go away in the ultimately, and then there'd be our friend d star d phi dy, right, equals 0. So there's our Hasegawa-Miner equation. Now, how would I form the energy for this? I wanted to derive an energy equation for this. Same way as before, you multiply by phi, right? So look what happens. You get d by dt of phi squared multiplied by phi plus rho s squared grad phi squared, and then plus everything else. By the way, here you notice v star times the bracket of d phi dy with phi. What is that going to be equal to? 0, right? The real part of that 0, right? Because I write this as sum on k I minus I ky phi k squared. So bam, goodbye. Anyway, this thing, look at that. That's clearly the energy. So here's our kinetic energy again. What do you think that is? This, which comes from that, is clearly, where did I write it? The same thing as, this. Here we go. In the limit of n tilde over n goes to, e phi over t, which is the Boltzmann limit. Has to be there. That's an internal energy, right? That comes from the density fluctuation. Here, the density does not appear explicitly since it's the Boltzmann limit, but it's the same term. And the drift wave involves both mechanical cross-field energy, right? Think about what the drift wave is. It's Boltzmann, fundamentally, at the simplest level, it's Boltzmann electrons and E cross B in polarization ions, right? Right? So Boltzmann electrons, what does Boltzmann mean? E phi over TE. There has to be, there has to be some internal energy in that. Right?
So internal means in the sense of thermodynamics.
Exactly. Yeah,
Okay.
that's why I call it internal. And it's clearer in the acoustic wave, because the acoustic wave, the mechanical energy is, of course, the kinetic energy. The internal energy you can think of as the potential energy, right? You compress something, then it pushes back. So the internal energy is the potential. But you can, if it helps you, you can think of, this as a kind of potential energy. Yeah. All right. That's a good question. Any other questions?
Why in the wave energy it doesn't concern the field energy?
Well, it does. Because what do you think this is?
is the kinetic energy of the
Well, I mean, I can think of it either way. It's good, another very good question. You can think of it as you can think of it two different ways. You can think of it as the kinetic energy of the E cross B motion, but I mean, look, what, you know, this is ultimately E perp squared. That looks like field energy to me, doesn't it? Right?
I think if the plus these two together,
What?
because the field energy and the kinetic energy are contained by different material. One,
Well, they're charged particles. Remember, it's E cross B motion, remember. But look, let me try something else on you.
I'm sorry, what was his question? What was
He's asking where is the, why, he's asking, you know, we're talking about wave energy. He's asking where has the field energy gone? Okay? So generally, he's right. I mean, I know it's
phi
another.
square is field energy?
What?
Phi square is field energy.
Field. No, it's not all the field energy.
What
I
do you mean by
mean-
field energy?
Well, there's some of the answer is there's. How would you calculate the total wave energy? You tell me, it's a good, right? Total wave energy density. How would you calculate it generally?
kinetic energy of the fluid.
Yeah, but there's a nice handy dandy formula. I mean, why think when you can plug into a nice handy dandy formula? What's the handy dandy formula?
E squared plus B squared.
Oh, well, B squared is zero. It's, you know, in other words, there's no, B is just a fixed constant here. There's no magnetic fluctuation in electrostatic drift wave. But the wave, the very fundamental point, the total wave
Kinetic
energy
plus
that-
potential.
What?
Kinetic plus potential. You want to say?
Well, relax, just let me write the thing, please, all right? What is the, you guys need basic course in plasma physics, okay? This is very, very fundamental point, okay? So how would you write for electrostatic plasma wave? There's a general expression for the total wave energy density. What is it? Well, I mean, look, it is
Yeah.
famous thing, d by d omega of omega epsilon evaluated at omega k, e squared, right, over 8 pi. Remember that? All right, well, get out your Landau and Lifshitz continuous media and read, okay? I think, I don't know if you look, it might be in my lecture notes from Physics 218A on the UCSD site. All right, it's, how to derive that. But that's a classic result. You should know that, okay? Right, now epsilon, the only thing that's a little tricky here is that epsilon for drift waves, you know, is equal to 1 plus 1 over k squared lambda debye squared, I think, times the ion susceptibility, this is a susceptibility, not a diffusivity, minus the electron susceptibility. You know, this is the proportionality, n is equal to chi times phi. This is a susceptibility, all right? And you're gonna have, and of course, k squared lambda debye for drift waves, as we were discussing the other day, is small, so 1 over it is large, so you drop the 1 and you just do that. Okay? So, but this ultimately, what is this gonna turn into when you do all the algebra? You can look, you're gonna see what happens here. Right, so, for epsilon, so total wave energy density. First of all, for a simple plasma wave, plasma oscillation, you have epsilon is equal to 1 minus omega p squared over omega squared. So of course omega is equal to omega p. Then omega d epsilon d omega, interestingly, is equal to 2. So the total wave energy density is equal to e squared over 4 pi. You know why it ends up as 4 pi instead of 8 pi? Because this is equal to, of course, e squared over 8 pi plus e squared over 8 pi. This is your beloved field energy. And this is the mechanical energy. Right? And if you just solve, dv tilde dt is equal to q over me tilde, you can see that. Right? So that factor of 2 has physics in it. Half of it is the field energy and half of it's the mechanical energy of oscillation. All right, so that's, the point. The total wave, this is not the field, this is the wave, is equal to the field energy, as you're asking, plus the mechanical energy that supports the wave. Okay. So the answer is it's in here, so you can, this contains, if you work this out for drift waves, in other words, this is going to be k squared phi squared. So this will cancel conveniently. You realize that this thing is going to be the dispersion relation, right? That this is going to be something like omega star over omega minus 1 minus k verb squared rho squared. If you work everything out, you will find that this formula gives the total wave energy density equal, and I'll do the normalizations, right, equal to np over 2 times e phi over t squared plus rho sub s squared grad phi squared, and everybody is happy. And this is grad of e phi over t. It's all there. Little homework problem, work this out, okay? So that contains the mechanical energy and the field energy, okay? If you wanted to figure out what the mechanical energy is, you could simply do something like mechanical energy equals total wave energy density minus, e squared over 8 pi, and go from there. Right? And that would tell you what the mechanical energy is.
So you mean the mechanical energy is much larger than the field?
Yeah, because it's E cross B, right? In other words, there's no, generally, there's and K rho is less than 1, so yeah. But this is an important concept. I would urge you to learn this. Right, and then there's the general issue of the pointing, the wave electrostatic pointing theorem, which sounds like an oxymoron. But, you have something like, you have essentially d by d, great black word, d by dt of the total wave energy, which is omega d epsilon d omega, evaluated on omega k times d squared over 8 pi, right, plus, then there's the wave energy, the divergence of what amounts to V group, right, times omega d epsilon d omega times E squared over 8 pi. Alright, so that's essentially that's the wave energy density flux. Right, and again, electrostatic waves have a wave energy density flux, because even though you might ask B tilde is 0, so how can you have a propagation of energy? The answer is it's the mechanical energy that's propagating, okay? And then, of course, there'd be something like the dissipated power, E dot J, and this, as you can imagine, ends up as something like E squared over 8 pi times omega times the imaginary part of epsilon. Okay, and that's a fundamental result. So I would urge you guys to dust off your Landau and Lifshitz and start reading. That's well worth knowing, okay? One of my favorite books, by the way. I wonder if anybody but the authors have read that book cover to cover. I've read a large part of it, but I have not read all of it. It's a difficult book in places, I have to say. It's quite challenging, very deep in places. I mean, he does like self-focusing in one page and all things like that. My bet is that no one but the authors ever read it. Maybe the translator. All right, any other questions? One of my favorite volumes in that series. Okay, so any other questions? You might as well ask questions, so I know we've got plenty of time. You have to you can't go too much over, so. Questions? All right, so let us talk a little about kinetic theory. I don't know. Anyway, tomorrow we're going to start wave turbulence, but we'll get as far as we get here. And then maybe sometime, because like today we have to sort of end, we can't go more than 10 minutes over, so. But we can continue next week. Maybe a little bit of extra someday. So, kinetic theory of drift waves. Now, based on what you know, and this is going to be the collisionless drift wave. And there's really, well, and this also leads to trapped electron modes, which are a variant of this. But if you understand the collisionless drift wave, the trapped electron mode is easy. So let's talk about the collisionless drift wave is less technical, more conceptual. And so trapped electron mode, you'll see papers called TEM. And it comes in two species, the collisionless trapped electron mode and the dissipative trapped electron mode. So you'll see that kind of abbreviation. So let's talk about the collisionless drift wave. So the collisionless drift wave, let me say this. The collisionless drift wave is quite analogous to the collisional drift wave that we discussed. Right, with the obvious replacement of the parallel diffusion is going to be replaced by, Landau resonance. And that's what's going on in trapped electron modes too. It's just that the Landau resonance gets a little more tricky because the field lines are curved. So could you guess the analogy? So, I mean, let's see, let's see the dissipation. Let's make a little table and see if you guys can figure out in advance where we're going. So we'll do the collisional and collisionless. Okay? All right, so obviously this is K parallel squared B parallel. What do you think the analog is here? Clearly K parallel B parallel, right? B thermal electron, right? In other words, instead of parallel diffusion, it's parallel streaming, okay? So the instability condition is omega minus omega star negative, and this continues to be the case here. The growth rate here, you remember, went as omega, gamma over omega went as omega over K parallel squared D parallel. What do you think the growth rate goes as here? What would you guess? You're about to say it. so-
Omega star divided by the K power,
Rethermal. Exactly, that's exactly. So you get gamma over omega goes as roughly omega star. There's an absolute value from the Landau resonance, but you're right, that's exactly. And there's, of course, a factor from the distribution function, you know, this kind of thing, since you have a Landau resonance, but, you know, for it's basically that, exactly. So, exactly, we'll derive it. And of course, you need, of course, this condition, so there's some factors of K per rho squared, just as we had here. You know, comes from the fact that the frequency, the omega has to be less than omega star, but it's the same bloody story, okay? And last but not least, you know, if you wanted to make a diffusion, you know, what would the correlation time, tau c in the diffusion, the step time, is 1 over K parallel squared D parallel. So the correlation time in the cross field diffusivity would be the parallel streaming time. Exactly. Very close analogy. Okay. So let's derive it. So as usual, I'm going to take the ions. As usual, we have the basic, you know, kind of phase velocity ordering of omega over K parallel in between the electron and ion thermal speed, okay? And at the 0th order, I'm going to let the ions be, you know, omega star over omega minus K per rho squared times E phi over T. And if you were trapped on a desert island and had to think, how would you derive that? Okay, from the Hasegawa-Niemann equation, or just continuity, plugging in the E cross B drift and the polarization drift, yada, yada, yada. Okay? So these are now the question is, what are the electrons? And the electrons are, of course, equal to Boltzmann, but there has to be a correction. All right. And now we turn to kinetic theory. And, you know, we're going to write the electrons as the integral over velocity of a distribution function. Which brings us to, sorry. I'll survive the day. brings us to then doing kinetic theory, we will use the drift kinetic equation. Which is effectively a kinetic equation for the guiding central motion. And it is, of course, basically based on the idea that the electrons, basically electron polarization, etc., where etc. would be finite electron gyro radius. In other words, K perp rho e are both negligible. So in its simplest manifestation, the electron drift kinetic equation is just phase space density is conserved along guiding center orbits. I'll write it in words, right? So the Vlasov equation is phase space density conserved along particle orbits. The drift kinetic equation is phase space density conserved along guiding center trajectory. So what equations specify the guiding center trajectories? So there's motion both across the field and along the field. What's the motion across the field for the electrons? E cross B drift, right? So the guy sort of basically says d by dt of x perp is equal to minus c over b grad phi cross z. I'm making it real easy, a straight field, nothing fancy, okay? What's the motion along the field, as in one dimension? So let's make the parallel the z direction. So it's dz dt is equal to dz, and then it's dvz dt is equal to minus magnitude E over mass of the electron, d by dz of phi, right? So it's the usual story along the magnetic field, right? So how would you write the equation for conservation of phase space density along electron trajectories, given these equations for the electron trajectories? Right? Well, it would just be, by the way, you'll note very conveniently that these satisfy Liouville's theorem, right? In other words, if you think of, a phase space, that basically the divergence of the flow in the phase space of this is equal to 0, because div perp dot x perp is equal to 0, and of course this is clearly Hamiltonian along the field. So everybody's happy. In a curved field, it's a little trickier, a little bit more, but that's another discussion. Can't do everything in one lecture series. So anyway, so you would write df dt is equal to 0. If we're not worried about collisions, right? So this would be d by dt of f plus, right, then v perp dot grad perp f plus vz d by dz of f. And then there's the nice thing about, you were saying we neglect the polarization and anything, there's no perpendicular acceleration. So the only acceleration is sort of A parallel times df dv parallel. It equals to 0. And A parallel is just dv dvz dt. So you'll notice we can immediately write the drift kinetic equation as df dt minus c over b grad phi cross z dot grad perp f, and this is a perp, make everybody happy, plus dz df dz minus e over the mass of the electron times ez times df dvz is equal to 0. And there's our friend, okay? And it's very important that all these wonderful stories of drift, and with a bit more complications, which I'm not going to go into, but these drift or gyrokinetic equations have the structure of essentially at the electrostatic level, and magnetic fluctuations are another matter. E cross B drifts across the field, and then kind of 1D dynamics along the field. In other words, the usual story. Okay, so here's our friend, and we will assume that F is some equilibrium or average distribution plus a fluctuation, just as we have an average density plus a fluctuation. And to make life easy, we will say this is a local Maxwellian. So if we, in general, F, for this stuff, it would be nice to have a bigger board, I have to say. So this is the usual assumption that the fluctuation dynamics are collisionless, but on some longer time scale, collisions enforce a mean distribution that's a local Maxwellian. So, F would be something like, n naught of radius times e to the minus mass of the electron v perp squared plus v parallel, or vz squared over 2, and here the temperature could be a function of position, right? And there'd be a normalization factor like a V thermal, since the temperature is a function of position, the thermal velocity is a function of position, and there'd be a factor cubed, and then there'd be some number here that you can worry about. So and then if you really wanted to be careful, you could in fact keep a finite current. So then you'd have a VZ, 0, a mean VZ, and that too could be a function of position. Right? And there is such a thing as a current-driven drift wave, which I think I will give you as a homework problem to work out, which is it's kind of
What is the energy?
what?
What is the bracket?
What bracket? F just means the mean or equilibrium distribution function. Mean.
Mean over time or
Mean over time or mean over theta phi, take your pick. We assume ergodic, so in other words, it's the two are equivalent. Okay, it's basically the unperturbed distribution function. So the point, gentlemen, is the gradients, because the gradients are the thing where, the energy is. The gradients are the gradient in density, and in principle, the gradient in temperature. and in principle, the gradient in parallel velocity, right? And here, this is effectively the gradient in current, when you're talking about electrons, okay, parallel. Okay? So, I mean, to make contact with the collisional drift wave, I'm going to say we'll focus on the density gradient rise. But I mean, the temperature gradient is important, I mean, too. So. All right? Yikes. Oh, we are not going to make it today on this. Anyway, let's do the best we can. Any questions? All right, so what we're going to do, we're going to linearize the bugger. So we're going to basically write df tilde dt plus vz df tilde vz is equal to minus, let's see, this is plus c over b naught grad theta or grad y of phi times df average dr, right? And I'm going to have plus e over me, right, times, because I went to the other side, and then I'm going to bring back a minus d by dz of phi times d by dvz of f average. Right, so that's my linearized drift kinetic equation. So all I'm going to do is, I want to basically get f tilde, and plug it in, to quasi-neutrality. And that will give us then the collisionless drift wave. Dispersion relation and growth. So you really should be able to do the rest of this as a homework problem, but I will take you some of the steps along the way. Okay? Then the other question later on, to calculate the fluxes, then you do quasi-linear theory on this thing. Okay? And this gets interesting because you have both a quasi-linear flux in space and you have quasi-linear heating, in this thing as well, so it makes it somewhat entertaining. All right. Now, we can rewrite this in some slightly clever way. So suppose I'm going to say, so T is, to make my life easier, T is homogeneous, in other words, grad T is 0, and V0 is equal to 0, right? So that means the only thing here is the density. That is, of course, in reality, the temperature gradient is extremely important, but they give me a small blackboard in this room, and I've got to fit it on one blackboard. So. All right, now, the other thing is F is, as you see, nearly a Maxwellian. So we can kind of write this in a slightly clever way. We can write F, right, as equal to E phi over T times F average, which is our friend of the Boltzmann relation, plus G, which is everything else. You realize, as before, that G is what matters. The Boltzmann relation doesn't do anything, okay? Right? So, because both its spatial flux is 0 and its velocity space flux is 0, right? You can show that for yourself very easily, because plug the Boltzmann relation into this, you will get 0. Okay? Because you'll have an IK parallel phi and a phi from this, so the real part will be 0. So if you plug, and this is, this I should write it as this, okay? So this is the perturbation. And you realize, of course, then that the integral over velocity of g, right, is nothing more than our friend h, the non-adiabatic part of the density perturbation, right? Okay. All right, with that little proviso, so I plug that in here, so I get d by dt of E phi over T times F average plus G tilde. And I get plus Vz d by dz of E phi over T times F average plus G tilde. Then I have on the right-hand side, I have C over B times grad y phi tilde times df average PR. And then I have over here, now we can be a little cagey, we can have minus E over the mass of the electron, and then we have d by dz of phi. And since we know this thing is a Maxwellian, we can get a minus Vz over V thermal squared, which is TE over ME, times F Maxwellian. And so that we can cancel this and this with that. All right, so everybody's happy. And then you further notice, and I should have a notational consistency, you have that. The other thing you notice is we can cancel this guy with this guy, right? Because I have a d by dz of E phi over T, a d by dz of E phi over T. I have a Vz here, a Vz here. So he goes bye-bye, and he goes bye-bye. And then, of course, I bring him to the other side of the equation. So I get d by dg plus Vz d by dz of g, right? And now you notice I have changed this to an equation for the non-adiabatic part, is equal to minus d by dt of E phi over T F average. And I would have plus C over B grad y phi times df naught dr. Now, gentlemen, does the right-hand side, notice now we have a nice equation for the non-adiabatic part. Right? So this is the name of the game in kinetic theory, is to work with an expression for the non-Boltzmann or non-adiabatic part. Again, that's the part that has all the interesting physics in it. It controls the transport, the heating, everything else. Does the right-hand side of that equation look familiar to you? It is an old and familiar friend at this point.
terms in Hasegawa
or Hasegawa-Wakatani. It looks, I mean, this G, remember, integral over velocity of G is just our friend H, right? So this is like the equation for H in Hasegawa-Wakatani, right? So then this thing is really omega minus omega star in disguise. Right? This thing, look, this is going to be, you know, I omega times E phi t over d times S. Right? And what's this? Well, look, we just do a little creative rewriting. We put an E here, a T down here, a T up here. What's df dr? Right? That's dn dr, right? And of course it's normalized, so, you know, so that's, right? Right? So then this cheerful little term ends up as minus omega star times f average times E phi over t. Right? So now, see, this is starting to look familiar, right? This is very similar to our friend from the collisional drift wave. Okay, you realize, by the way, that if you want, it's a little bit of arithmetic, but if you're serious about learning something, you might consider the case as if there was a temperature gradient. How would a temperature gradient modify that? Is an interesting question, okay? You can work that out for Homer. It's quite straightforward. All right, so what do we got? We can rewrite this equation in k-space as, you know, minus, let me do this. Actually, I can gain some space here because time is becoming a factor. So in writing in Fourier transform, you have minus I omega minus kz vz times g of k omega is equal to I t over t omega minus omega star n, okay, times f at times phi of k omega times f average. That's the linear response for the non-80. So this is the linear response for non-adiabatic distribution function, right? Remember, what we're going to do is, you know, let me fill this in here. I'm going to write basically omega star over omega minus k per rho squared is equal to 1, or plus, you know, basically the integral d cubed v of delta g of k omega delta phi. In other words, the susceptibility there, right? So they're going to plug that into a dispersion relation. Okay. Omega star n is the usual thing with the density gradient. So omega star n is what? It's k theta rho s cs over L sub n. Now why don't you work out the correction for grad t? so what happens with grad P is that omega star n goes to omega star n times 1 plus this parameter eta sub e. And it's a function of velocity, v parallel squared over 2 plus v perp squared over 2 minus 3 halves. That's right. And eta e is in some sense the ratio of the temperature gradient to the density gradient. Right, so that's interesting. It makes this thing then becomes a function of velocity with the temperature gradient. So that's a little homework problem for you. It's not hard. All right. So what do we do with this? So you see what's coming here. So we immediately write g of k and omega is equal to minus e by k, or the omega over t times f average times omega minus omega star over omega minus k parallel v parallel, right? And there is our linear response, right? That's the basic linear response for the electrons for the collisionless drift wave. Time is moving, unfortunately. Any questions?
Where is the part of the F?
Oh, no, the F is homogeneous in Z. I mean, Z is like the toroidal direction. So you say, in other words, no, it's a good question. I mean, I was going too fast, right? Always, we're assuming that the average distribution function is homogeneous in the toroidal direction and homogeneous in the colloidal direction. Really, we're at this level, we're doing a tube and not a torus, you know. That is, yeah, exactly. Now that, by the way, when you have, you know, in reality, getting back to visits from my boss is named Lee too, a different Lee. You know, he wants to talk about resonant magnetic perturbations. In other words, these are coils put on the machine for reasons of controlling Elms, which is the hot topic of the day, and they break symmetry. So then you have to start worrying about things like that. In other words, the equilibrium becomes three-dimensional. So that is a little bit of a challenge. But anyway, first let's talk about the basic things. So what do we do, right? So that means the basic drift wave dispersion relation then, which I think unfortunately we'll have to stop here, is omega star over omega minus k perp squared rho squared, and this is equal to 1 plus the integral d cubed v, and then we can pretty much read it off. There'd be a minus sign here. There'd be an F average, which is our friendly neighborhood Maxwellian, and there'd be omega minus omega star n divided by omega minus k parallel v parallel, right? And there's our basic dispersion relation. Okay? So at this point, I think, you know, we're going to be, you know, we're interested in the case of, you know, again, omega over k parallel less than v thermal electron, so you know, it's pretty easy to work out from here. So maybe since we've run out of time, it's well after 5, I'll just, if you're energetic, try to derive the growth rate from this point, just as we did in the other case. Try to derive the growth rate for the collisionless drift wave, okay? That'd be a good little homework exercise for you.
A stupid question about nomenclature.
Yeah.
When you say drift kinetics, you just explicitly put the velocity and the force into the Laplace equation. So you call it drift kinetic?
Yeah, I mean, I don't know, it's a kinetic I don't know where, look, I didn't make the nomenclature, so don't blame me, okay?
No, I'm not.
No,
I
I
don't,
mean,
I don't understand. Just why? What's
it's
new?
why the name?
Yeah, what's new? I mean, in drift kinetic compared to Vlasov or.
Well, yeah, it's reduced description. Vlasov description is deriving the full orbits in a six-dimensional phase space.
Yeah.
Drift kinetic equation reduces the phase space to, I guess, 4 dimensions, right? In other words, at
What is
z.
reduced? I'm sorry.
What?
Can you remind us what is reduced?
There's no, look, there's no velocity scattering here, right? In other words, the full Vlasov equation is df dt plus v dot grad f plus q over m, times e plus v cross b naught,
Yeah.
right, dot df dv equals 0. So you're keeping track of v perp, you're keeping track of the gyro motion phi, right? You're keeping track of vz. You're also keeping track of the radius, right? So we say x, y, and z, right? So in drift kinetics, this is gone entirely because you're just following the guiding center, right? So the gyro phase is gone, and there's no more dynamics in this. This is in a sense partially gone, right? It's just a parameter, right? So in some sense, you're really working in a 4D phase space with v perp as a parameter, Now, the f average is a function of v perp, but there's no evolution of v perp. It's fixed at whatever it is. So you gain a lot. In particular, for the electrons, you get rid of the fast electron cyclotron motion. So you completely you get rid of that at the get-go. So it's a reduced description.
Approved. Okay.
Okay? It's essentially, it's a Vlasov equation for the guiding center density as opposed to the Vlasov equation for the particles. Okay?
What is
And it is the same thing as the gyrokinetic equation in the limit of k perp rho e go to 0, to answer your other question. Okay, it's, I think, quite intuitively clear what's going on here, right? And this, the whole point of these drift and gyrokinetic equations is to reduce the description. So this is maybe the simplest case, since there are really drift kinetics is easy because basically the particle essentially is so well approximated by the guiding center that you don't have to worry about the electron polarization charge. The ions you do. Any other questions?